Good day. So, today we will have the second lecture on the physical medium. In the last lecture we have seen the different ways this digital signals and analog signals etc., how they can be used for communication, how digital data or analog data can be encoded into, well, we are mostly interested in the digital form of data. So, how they can be encoded etc., and some of the general impairments of a physical medium we have seen. In this lecture we are going to look at specific media which are used in networking. Okay. So, there are basically two types of media which are used for communication. One is cable. I mean there are two different classes altogether. So, one is a cable. Now, this cable could be some copper cable, they could be coaxial cable or twisted pair or shielded twisted pair. So, the twisted pair, I mean we sometimes they are actually unshielded twisted pair or UTP, and sometimes we simply call them twisted pairs since they are more common. There are shielded twisted pairs also. And then of course, the one of the most important cables these days is the fiber optic. So, these are the different types of cables that we use in networks. Similarly, we can also communicate without the use of any cable by simple electromagnetic radiation, and this radiation could be in different ranges of the of frequencies, like they could be infrared or microwave or radio or satellite etc. So, we will look at all these one by one. First, let us look at the kind of media that we use in a LAN. LAN, as you would remember, is a local area network, and a local area network could vary from, let us say, 1 meter to 1 kilometer. So, it is local strictly by some means of its size in some way. So, 1 meter means 2 computers connected residing on the same table, connected side by side. It could be all the computers in one building and all the computers in several buildings and so on. So, that is a kind of range that we have for LAN, and the medium that we use for a LAN, they could be coaxial cables, UTP, fibers, wireless. So, you would note that basically most of the types of cables that we talked about find their way in some niche or other in local area networks. And of course, UTP or unshielded twisted pairs are of different varieties, so or categories. So, that CAT is for categories. So, we could have CAT 3 cable, CAT 5 cable, CAT 5E cable, CAT 6 cable, CAT 7 cable and so on. You must have seen CAT 3 cable if you have looked. All your telephones, that means the landline phones, they are connected by unshielded twisted pair cables of category 3, all right. For computer networking, I mean CAT 3 cables could also be used for LAN, although we usually prefer CAT 5 onwards. And the kind of things that are on the network, that could be your PBX. PBX is your local telephone exchange, that could also have some digital ports etc. Ethernet is one technology which is used in LAN. ATM is also used. FDDI is sometimes used. FDDI, if you remember, is fiber distributed, that is that FDDI ring kind of structure. We have network boxes like hubs, switches, routers etc. So, these are the terms you would come across. Of course, we would talk about some of these in more detail later on, but these are the some of the technologies that come into LAN or local area networks. Then we come to slightly bigger networks called MAN or metropolitan area networks. Of course, there are some networks which are even smaller than a LAN, okay. They are called personal area networks, some networks. So, I may be wearing 3 or 4 computers and they are connected in a network on my body, okay. So, we will come to PAN later on, but going on the other side of the spectrum, that means from LAN to a bigger network, which is a MAN, that is a metropolitan area network. Typically one campus or one city maybe several small towns which are close together, they would come under the purview of a man. So, man would so a very rough ballpark figure is, say, man would be extend maybe about 10 kilometers. So, it could be 5 kilometers, it could be 20 kilometers. So, something in that range. And the kind of medium that we use for metropolitan area networks are coaxial cables, both baseband and broadband. We will come to these what they are. Once again, sometimes UTP are used, but that is not very preferred way of connecting, although UTP are used. One way where UTP is definitely used are when you try to network through telephone lines. That is, I mean, telephone lines, as I told you, they use UTP. It could be a hybrid kind of system. Okay. Some part of it could be coaxial, some part of it could be UTP, and some part of it could be fiber. Okay. Fiber means fiber optic cables. And the kind of things, of course, that the kind of technology that goes into a MAN would be PBX, different kinds of modems. For example, if you are using a broadband coaxial cable, you might use something what is known as a cable modem. Then you have this long reach Ethernet, that means Ethernet on the over maybe some lines, cable TV, DSL, digital subscriber lines, or it could be wireless. One issue which is important in MAN is the issue of access. All right, that means how do you reach to each individual users? I mean, think of a town or a city. So, you really have to, in order to network the entire town, you have to reach to each individual residence, and reaching to each individual residence involves cost. Okay. If it is a small building like in a LAN, you can take very good say UTP cable to his room. Okay. Now, there are problems of taking UTP cables to each individual house. I mean, there could be, I mean, electromagnetic disturbance and things like that. But apart from that, there is a question of cost. Okay. If you are trying to build so much copper into it, that is quite costly. So, how to access to users who are distributed over a somewhat wide area in the sense of several kilometers, that is an issue in metropolitan area networks. And finally, at the extreme of the spectrum, we have WAN, that is wide area network. So, they may stretch from 10 kilometers to maybe 10,000 kilometers. Okay. So, 10,000 kilometers or almost to the other side of the globe. So, they may involve very, very long distance. Medium is usually fiber or satellite, and the kind of technology that is used in WAN are SONET or SDH. They are the almost similar technology. ATM, IP, that is the Internet Protocol, DWDM, dense wavelength division multiplexing, GEO and LEO. GEO stands for geostationary satellite, is a short form of geostationary satellite, and LEO is low earth orbiting satellite. So, these are the kind of technology that goes into WAN. And the issue in MAN, one issue in MAN is of course always cost and bandwidth. WAN bandwidth, because as you can imagine that when you have to take some message across hundreds or thousands of kilometers away, there is a lot of cost involved in it. All right. So, WAN bandwidth is usually costly, and we try to make the maximum use of this bandwidth. Of course, in recent times a lot of fiber has been laid internationally. So, the bandwidth problem is becoming less and less, but even then WAN bandwidth remains costly. Okay. Now, let us see at some of the cable specifications that we use. First, we take up this UTP cable of category 5. So, Cat 5 UTP cable, their specification says about 100 megahertz, and this can stretch up to 100 meters. Well, these are the figures which are normal. Okay. You can stretch things a little bit this way, that way at times depending on your operating circumstances, etc., but this is normally the figure. So, some kind of idea you can have from these figures. and the connector. So, the way the Cat5 cable also UTP also looks like your say almost like your standard telephone cable, only thing is that they are made in a slightly up to slightly better specification. The connector at the end of a Cat5 cable that has got a specific number assigned to it, that is called RJ45. So, you use RJ45 connectors for connecting Cat5 cables. There is a standard ANSI or TIA or EIA standard for how Cat5 cable used to be used, what are the standard way of how they are twisted. There are a number of wires inside this twisted pair of cables. So, which wire stands for what, etc. So, all these things are there in the standard. So, I simply refer to the name to the number of the standard here, which is EIA 568A, and then a cable has to be tested according to some standards. So, TSB 6795, these are standards for testing cables. Okay. And so, Cat5 cable is usually under these circumstances, that 100 megahertz to say 100 meters. So, if you are within that 100 meter, it is expected that if you have done everything properly, it is expected that it can work up to 100 megabits per second. Now, the point is that if the distance is much less than that, then naturally the same fiber the same cable can work for work at a much higher speed, alright. So, inside the same room a Cat5 cable may be used for a 1000 megabits per second connection between computers or network nodes. Then there is some enhanced version of Cat5 cable. So, I mean I will not go into the details of this which are given over here. The specifications are almost the same, only thing is that it is slightly better in some way, and it can work for 1000 base TX for small distance. So, for as I said that within a room, if you are using Cat5 E cable instead of Cat5 simple Cat5, you may be able to operate at 1000 megabits per second without too much of a difficulty. And then we have the Cat6 cables, so which is again slightly higher than Cat5 cables. Here the specification is 250 megahertz. So, this specification is much higher. So, naturally Cat6 cable would be somewhat costlier than Cat5 or Cat5e cables, the same kind of connector, and it is actually the recommended cable for operating at 1000 megabits per second. So, here is a point, when computer networking started, okay, people used to think that 10 megabits per second is fairly high speed. Okay. Soon people were really using networks a lot, and 10 megabits per second was not enough. So, people went to 100 megabits per second, and now people are saying that okay, 100 megabits per second is slow. So, we want to go to 1000 megabits per second. So, you see that in a comparatively short period of time, maybe 15-20 years, we have sort of the demand for bandwidth has grown 1000-fold. So, when you are planning for an infrastructure, say copper infrastructure in any organization or somewhere, then you should keep this in mind that whatever specification people are giving to you today, okay, after some time people may want to upgrade, all right. So, if you can, of course, if you what I mean to say is that if you put in Cat6 kind of cable and use it for only 100 megabits per second today, and then 1 or 2 years later you can use the same cable for 1000 megabits per second, saving a lot of cost at that time, all right. But of course, that would mean an upfront more cost today. So, that is always there. So, for testing these kind of cables, there are all kinds of testing parameters. I will not go into the details of this at all. So, this is a rather technical part. but say return loss is a measure of the reflected energy caused by impedance mismatches in the cabling system. So, when you put a cabling system you can test it, and one of the things you might test for is the return loss. Another thing you might test for is a crosstalk, that ELF EXT, that is a crosstalk as reflected from the other end. So, ELF LFX is defined as the measure of signal coupling from a transmitter at the near end into a neighboring pair measured at the far end relative to the received signal level on the same pair. So, these kinds of testing parameters are there. So, for testing copper cables, similarly if you have put say fiber optic cable somewhere, then fiber optic cables would have some other testing parameters. So, it is a good idea to test the passive networking infrastructure, meaning all these cables and connections etc., and how they perform. Now, we from unshielded twisted pair cables we go to the baseband coaxial cables. We have already mentioned about baseband coaxial cables. These are the cables we were talking about when we talked about that bus topology, if you remember. So, it is basically this is a shielded cable. So, there is a copper core surrounded by an insulating material which is surrounded by a braided outer conductor, which is surrounded again by a protective outer covering. So, this is considerably thicker than let us say an UTP. And then in the coaxial cables also there are two varieties, the so called thick coaxial cable and thin coaxial cable. Once again this technology is slowly is becoming almost obsolete now, but just for our knowledge sake, a thick coaxial cable, this is represented also as 10^5. This 10 represents that it works at 10 megabits per second, and 5 represents that it can go up to 500 meter. The thin coaxial cable is 10^2. So, it works at 10 megabits per second and goes up to 200 meter. As I told you, nowadays almost everybody wants 100 megabits per second to their desktop, in which case this thick and thin coaxial cables, that is the baseband coaxial cables, are no longer of much use today. But another type of coaxial cable which is very much in vogue and which is being laid even today, that is the kind of cable that your cable operator puts, all right. Now, you know that many of you have seen that cable operator puts some kind of a coaxial cable into your room which goes into your TV. Now, it is possible to use this same infrastructure for computer communication also, that is computer networking also. Remember that I told you while discussing MAN that one of the most important issue in metropolitan area network is the issue of access, that is how do you reach to each individual subscriber at his or her home. Now, this cable operator has reached a lot of homes anyway. So, naturally people started thinking that whether we can use these cables from the cable operators for network communication, and special kinds of modems were designed for that called cable modem. So, we have a broadband cable infrastructure rather than the baseband that we were talking about, and this is quite often used, and even now they are being deployed in many cities for computer communication. Of course, this is as I said analog cable carrying TV signals and are being used for carrying data traffic. Older cables carry up to 450 megahertz, and the newer cables that are being put can go to higher frequencies, that means higher bandwidth, and these cables also there is a point that these cables use amplifiers at regular intervals. Now, these amplifiers in the old days were only one way amplifier, because the way the cable operators wanted is that they are sort of broadcasting their signal from some central location and it just has to reach people's TV. but when you want to use this for computer communication, the communication has to be two way. So, the amplifiers also has to be two way amplifiers. So, such small technicalities are there. So, anyway it requires amplifier at regular intervals and is a shared medium, that usually this medium is shared, that means you and your neighbors, all your data is in the same medium. So, as I said, for carrying data two way amplification is necessary. Dual cable systems are like two trees both rooted at the head end. The head end is where the all the service providers equipment etc. are placed. So, there are all kinds of sub split systems, they use 5 to 30 megahertz for inbound traffic and the rest for outbound traffic, mid split system, and there are all kinds of systems for using this for data communication. By the way, there is also some asymmetry that people have found out in the usage of in the network traffic for an average user in a city, let us say. Because one of the most popular uses of computer network nowadays we know is just going into the internet, maybe surfing it, maybe getting some information etc., where the amount of traffic in terms of query etc., which flows from the user to the computer wherever it may be, that is relatively small, whereas you may be downloading large files, images, maybe even songs, movies etc. So, your bandwidth requirement, the upstream bandwidth requirement and the downstream bandwidth requirement, they are usually not the same, there is an asymmetry there. Now, we come to the another very important kind of cable, having looked at copper cables, namely optical fibers, all right. So, optical fiber basically is made of glass, very pure and very transparent silica glass is used. It is very transparent in the sense that it can go up to tens of kilometers without too much of attenuation on the way. So, think of a glass slab which is several kilometers thick, and you can see through it quite easily. So, it is that kind of transparency you require. So, naturally you have to there has to be some very strict standards in making this glass, but after all it is simply a glass which is drawn into a fiber for giving us this optical fiber. At moderate dimensions, light is restricted to the fiber because of total internal reflection for ordinary light. This is called a multimode fiber. At still smaller dimensions, say something like 8 to 10 nanometers, the fiber acts like a waveguide for lasers. So, this is known as a single mode fiber. Okay. Multimode fibers are used for maybe local area networks, whereas in all wide area networks and even in local area networks these days, single mode fibers is the more preferred way of carrying signals. So, finally, what is optical networking? One thing is naturally optical transmission. By the way, optical transmission could be fibers or free space. Free space means suppose you direct a laser from the source to the destination. So, on the free space. So, light will travel straight, or it is expected at least to travel straight and then reach the receiver. So, you do not need any fiber or anything at all, but there is a problem. First of all, of course, the first obvious problem is that the sender and the receiver has to be on the same line of sight without any hindrance in between. Okay, that is one point. And then there are other complications which might come in the sense that the intervening air may get hot and its refractive index may change. So, the light may actually bend like they do in a mirage in a desert. So, that kind of things may happen. So, it might miss the receiver altogether. So, all these things are there. So, for free space optic communication is not very much preferred. So, people prefer to put fiber optic cables wherever they can. So, these cables or free space, this is talking about the fiber optic transmission. Then there is a question of optical switching. Can we switch, can we provide the network level functionalities in the optical domain itself. So, this is a topic of research these days, as this is quite promising. So, maybe we will just look at a little bit of it later on. And finally, why optics? The point is, optical fiber capacity is huge, very huge. You see 50 terabits per second is mentioned over here. The point is that this is got a absolutely fantastic kind of a bandwidth. So, if you can put a fiber optic connection between two endpoints, your present as well as foreseeable future requirements will surely be met. Okay. So, that is one good thing about optics. The other very good thing about optics is that it is immune to electromagnetic interference. Okay. If there is a maybe a lightning strike nearby, even then it is not going to affect this very thin strand of glass that we have put, and which is very good, because had this been had the same thing happened to a copper cable, it would a surge would come and it would maybe burn off some of your equipment. So, this is another reason why we are very why people favor fiber optics a lot. Now, the point is this 50 terabits per second bandwidth that we were talking about, this is only theoretical, all right. Actually, sometimes I have been asked that what is the bandwidth of this fiber optic cable. Actually, this really does not make too much of a sense, because the bandwidth of this any fiber optic cable you would find would ultimately be dictated by the kind of boxes that you connect to it. The limitations would be there, the limitation is not inherent in the fiber. So, fiber can take up a huge bandwidth, as I just mentioned, but your end at the two ends you will have some optics and then you will have some electronics. Now, electronics cannot work at that kind of speed, a single piece of electronics certainly cannot work at that kind of speed. So, the overall speed or the bandwidth that you can get out of this fiber would depend on the kind of electronics that you put at the two end. That is why there is a lot of interest these days that whether some of these electronics can be replaced by optics, so that we can get much higher bandwidth. Okay. Now, and not content with just sending data through only one wavelength through this fiber, we have what is known as wavelength division multiplexing. That means different wavelengths of light carry different signals through the same fiber optic channel, that is called multiplexing. We will come to WDM later on. So, with this WDM you can get higher kind of bandwidth. So, Lucent for example demonstrated 64 lambda, that means 64 different wavelengths into 40 Gbps, that each of them operating at 40 gigabits per second over a distance of 4000 kilometers. Okay. So, I think that is really great. There are two kinds of wavelength division multiplexing, namely coarse wavelength division multiplexing, which is somewhat cheaper, and dense wavelength division multiplexing, which is used in WAN, but they are much more costly. So, we have the number of wavelengths that we can use today varies from maybe 8 or 12 to maybe 60, 64 or so. People are working on this ultra dense wavelength division multiplexing, which can carry us to maybe 100 wavelengths in the same fiber. For a quick history, in 1958 laser was discovered, then mid 60s guided wave optics was demonstrated. In 1970 the production of low loss fibers, because we want this low loss, and we will talking about this loss presently after some time. So, this made long distance optical transmission possible. Once again there was the invention of semiconductor laser diode, which was important. Then in 70s to 80s we used fiber in telephony in the form of Sonnet or SDH. Once again do not bother about what they are right now, we will be talking about them later on. In mid 80s LANs and MANs were sort of being put in place, and in late 80s we had a breakthrough in optically amplifying optical signals, all right. So, EDFA, so that is erbium doped fiber amplifier, we will be talking about that too in this lecture itself. and then in mid to late 90s this dense wavelength division multiplexing systems started being put, and in late 90s and in the 21st century. So, optical switching systems, different components of optical switching systems are being developed all the time. So, the point is this fiber optics has such a tremendous potential that there was a lot of interest in this, and there is a lot of work going on in this area at the moment. So, here is a some kind of a picture of a cross section of a fiber optic cable. As you see that when you see a fiber optic cable, of course, you will see this fat jacket, which is just a protective jacket, may be made of plastic, rubber, something. Then inside it there will be a glass fiber, but what you see is actually not the fiber, that is also actually a cladding, but that is made of glass. And inside this cladding there is this very fine core which actually carries the signal, and in one fiber optic cable like this you will have several such individual fibers. So, these are all individual fibers, the what is being shown over here. So, these are the individual fibers and each of them will carry one. So, one cable like this may, I mean, of course, we have shown only 3 over here, but it is typical to have something like maybe 4 cores, 8 cores, 24 cores, 120 cores in one cable, all right. So, let us look at this diagram of how it is. So, if you take a cross section, there is cladding on the two sides and core in between. So, if you sort of cut it sideways, so this is the kind of picture you get, and what happens is that once the light comes into the core, it I mean it sort of refracts like this and it impinges on this wall at a very wide angle of incidence. So, and there is a difference in the refractive index between the core and the cladding, okay, that is always maintained. So, so that the the point is this core is at a higher refractive index and this cladding is at a lower refractive index. So, this sort of reflects, there is total internal reflection over here. So, even if the fiber bends a little bit, although light usually would travel straight, but through this total internal reflection it would follow this fiber and small bends it can take and come out of the other side of the fiber. So, that is actually, but of course, there are I mean limitations to how much you can bend. First of all, if you bend this core too sharply, then this core will get damaged. So, there are sort of limitations on what is your bending radius, etc., radius of curvature, etc., but the in general through this total internal reflection the light will follow this core. So, this is another picture. So, light is input from one end. So, this sort of follows the fiber and gets out of the other end. Now, how do you I mean well the light gets out, but how do you get it into something, that means how do you connect these fiber cables, these which are actually glass fibers, how do you connect them to other things? There are two ways of termination. We can terminate a fiber by plugging it into a fiber socket and then sort of crimping them together. We can splice them mechanically by putting the two curtains into a sleeve and clamping them, or we can fuse them to form a solid. So, which is this is of course better method of connecting fibers, we can fuse them. Even when you fuse them, what will happen is there will be some kind of disturbance at that the material, that glass material will not be totally homogeneous at the junction. So, you will still there will still be some loss over there, but this is this loss is quite low if you are very careful in this splicing. And what about light sources? We have two different light sources, the so called semiconductor lasers and light emitting diodes. So, naturally the first one gives out lasers, whereas the other one, the simple LEDs, they give I mean non-coherent light. So, they are simple LEDs. So, both have their advantages and disadvantages. So, here they are. When you are using I mean the semiconductor laser as you know is coherent light, and whereas LED, simple LED gives you non-coherent light. So, the data rate for lasers, we can go to much higher data rate with lasers, and this is low. Fiber type, you can use multi-mode fibers over here, and you can use single mode fiber. You have to use single mode fiber. Usually we prefer single mode fibers for lasers. The distance that an LED can cover is short, whereas distance that a single mode fiber, that means a laser can travel through a single mode fiber, that is really long. So, all our long distance cables are actually these this type, single mode type, and they carry laser. And since we are going to higher and higher speed all the time, so we tend to prefer single mode fibers these days. And lifetime, of course, LED has a very long life. So, this is one area in which LED is definitely better, whereas laser, that lifetime seems to be short, although not very short. Okay, they will, I mean if proper care is taken, they will certainly run for several years. The temperature sensitivity for LED it is minor. So, for semiconductor laser it is substantial. So, this light source has to be maintained at a particular temperature. LED naturally is low cost, laser is more expensive. So, these are the pros and cons of the two sources. Now, let us take a closer look at the kind of losses that we have in fiber. Okay. Remember, when we were discussing about transmission through, let us say, some say electrical transmission through some copper medium, we were talking about it in the last class, that there are several kinds of distortion to the signal comes in. First of all, the signal strength tends to weaken as we go longer and longer distance. So, that is called attenuation. The same thing would happen in the case of fiber also, in the sense that as you go farther and farther, the signal will get weakened. You can look at it this way, that if the signal did not weaken, then we can look through a glass of any thickness. Okay, that is not true. The transparency of the glass, although it is very highly transparent, it is not 100%. So, that is why as it travels down the fiber, its strength will become lower, and not only that, it will also get, its wave shape will also get somewhat distorted due to certain phenomena. For example, there is this phenomena of Rayleigh scattering. That means, due to slight changes in the refractive index of the glass, some of the light will get scattered. Okay, then there are other kind of scattering called Mie scattering due to imperfection of the cylindrical structure. So, these losses are non-uniform for different wavelengths. So, that is why on the other end your signal will arrive first of all weakened, and secondly in a slightly distorted fashion. This figure, this famous figure is really a plot of the loss that light will that will happen to a light signal at different wavelengths. So, as you can see that say there are this loss in the fiber, this is given in dB per kilometer, that is not uniform. Okay. You can see that is not uniform across all the wavelengths. So, there are some wavelengths, namely here on the where the loss is very low. Okay. Then there are other wavelengths where the loss is quite high. So, what we do is that we try to find some kind of windows where the loss would be low and we can go to high distance, because remember that if the loss is low, we can go much longer without any amplification or repeater kind of action, and that is good. I mean, that would make the thing cheaper, and of course, we would be able to carry data through a longer distance. So, these are the three useful windows, so to say. One is the 850 nanometer window, the other is the 1300 nanometer window, the other is the 1550 nanometer window. So, around these wavelengths, okay, if we send our signal, then that will go a long way. So, these are the 3 windows which are used for data transmission. Because of the very high frequencies involved, okay, so you can look at the frequencies from that from these wavelengths you can calculate, you will see that the frequencies are very high. So, the theoretical capacity, so this because the frequencies are very high, it can potentially have a very huge bandwidth. So, the theoretical capacity of the fiber is very high, it is limited by the optoelectronic devices and boxes at the 2 ends. Now, let us just see that if we want to take the fiber optic signal to a long distance, naturally I mean whatever window you use, after some distance, okay, depending on what kind of source you are using, what kind of frequency you are using, what quality of fiber you are using, it may be 5 kilometers, it may be 50 kilometers, but when you are going thousands of kilometers, the point is that at some point of time the signal will become very weak. So, you need some kind of a repeater function. A repeater, what is a repeater? That will take in the incoming signal, amplify it, maybe make the shape all right. So, there are all kinds of repeaters, repeaters of different gates. There are some repeaters which simply amplify the signal. There are other repeaters which can also make corrections to the shape of the incoming signal, etc. So that so you need this repeater function in order to go to a very large distance. So, we will just take a look at this interesting phenomenon, that how do we repeat optical signals. So, optical signals travelling for long distances through fiber needs to be strengthened. This may be done through OLTs. Now, what is an OLT? That is an optical line transmitter which takes the signal to the electronic domain, and now of course, then you can use a fresh source over there to push the to make a nice and strong waveform and push it for the next leg of its journey. But this may be the important thing is that this may also be done in the optical domain, and the advantage of doing it in the optical domain is that you are no longer restricted by the bandwidth limitations of electronics. So, you can really operate at very high speed at very using if you are always in the optical domain, and one way to do that is this erbium doped fiber amplifiers. So, erbium is has a large number of excited states, and from some of the excited states it gives out say 1550 nanometer light, exactly the wavelength used in the third window in the glass. So, a few meters of optical fiber is doped, that means a small quantity of this erbium is introduced in that glass, is doped with a few parts per million of erbium and is pumped with 1480 or 980 nanometer laser to give amplification. So, what would happen is you look at this, suppose this is the ordinary fiber which is carrying the signal, and there is some portion of it which is doped with erbium, and a pump laser of certain frequency is fed into this. So, what will happen is that the erbium in this region, the erbium atoms in this region will be in an excited state. So, erbium will be in an excited state. So, when the signal photon comes, this sort of induces this erbium to come down to the ground state, giving an amplified signal. So, this is the very simplified version of how erbium doped amplification is used. Okay. So, there are other kinds of this thing. So, depending on what kind of pump laser you are using, you may go to this kind of excited state or this kind of excited state, from which you can go to excited state 1 and so on. But anyway, the basic idea remains the same. Now, because of dispersion, that is chromatic dispersion and polarization mode dispersion, wave shaping is necessary after some distance. So, there are other there are kinds of combination of waveforms known as solitons. So, these are waves shaped specially to match the dispersion characteristics of fiber, so that a soliton would not be distorted for a long distance. Distortion can also be counteracted by reverse fiber. So, all kinds of technology are there, we do not have the time to go into the details of this, but this is a very upcoming and growing field. So, once again why we like fiber? Because repeaters are needed only every 50 to 100 kilometers as opposed to maybe 2 to 5 kilometers for copper, not affected by power surges, electromagnetic interference, power failures, corrosive chemicals, etc. And two fibers, well, fibers by the way, a fiber communication in a fiber is usually simplex, that means there is a source on one end, a receiver on the other end. So, in one fiber the data is really going in one direction. So, for two-way communication we require a pair of fibers, alright, but these two fibers have more capacity than 1000 strands of twisted pair, and that is really great. Okay. And just one quick look at where fibers are going. Actually people are putting fiber at a feverish pitch now. One is the ultra long haul, that means distance maybe thousands of kilometers we have fiber. Then in the long haul we have this WDM or SONET, SDH, etc., which is put by the telecom companies or other communication companies. So, they are there. Then we have the WDM, ATM, SONET, Ethernet, etc., in the metro, that means within the same city. And now finally fiber is finding its way in the access side, that means to individual users also. And these are the different sort of ways fiber can reach a home, which is the ultimate goal of networking, which is that either you can take individual fibers to homes, or we can take them to a switch which is placed in the neighborhood, and from there individual fibers should go to every home. Or there is also a concept of passive optical networking, that instead of keeping a switch out in the open like that, so you put a passive sort of splitter which splits the signal into so many parts. So, the so called PON, passive optical network, that is another possibility. Okay. Now, let us come to the other most important way of most important physical medium, namely wireless. One disadvantages of each of the data transmission methods that we have seen so far is that they are all wired connection. Okay. So, moving from a wired connection to a wireless connection results in the ability to connect a network without having a physical connection. And what is the great advantage of that? The greatest advantage of course is mobility. That means, if you are connected in a wireless fashion, you can move around, but still remain connected. So, this entire electromagnetic spectrum, a lot of it is used for communication. So, this just shows a picture of that. So, on the low end we have the radio, followed by microwave, which is of higher frequency, followed by infrared, which is of still higher frequency. Then we have the visible light, of course we talked about fiber optic, and this part has not been used for communication as yet. Okay, maybe in future they will. Okay. So, these are the kind of frequencies we have. So, the frequency range is tremendous, from 10 to the power 4 maybe to the 10 to the power 14, 15 or so. So, we have these twisted pairs in this region, coaxial cables, maritime signaling, AM radio, FM radio, TV, terrestrial microwave, satellite, fiber optics. By the way, this radio, sometimes TV also, terrestrial microwave, satellite, they are all used for computer communication also. So, these are the different names for the different ranges. We have LF for low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, extremely high frequency now and so on. Transmitting data. Now, data is transmitted through a wave just as with the coax. Okay. That means, the higher the frequency, the more the data that can be encoded and transmitted. A narrow band is often used as the number of watts per hertz is high, that is one thing. And there are different pros and cons at different frequency bands. Okay. We will just look at some of them. Sometimes a wide band is used. Using a wide band allows the transmitter to jump from one frequency to another in order to avoid communication jams and to hide detections. Okay. That is just one example. and this is nowadays used in so called IEEE 802.11, which is a wireless LAN standard. We will look at this later on. Bluetooth is another wireless LAN standard. Okay. Now, to start at the low end of the spectrum, at the radio transmission, this is very easy to generate, travels long distances, it is omnidirectional, that is very important. That means, you have an omnidirectional antenna and you send your signal over there. So, it will travel in all directions, it will reach everybody around in a certain area. That will not happen in, let us say, if you are using a very high frequency like a microwave. So, at low frequencies, wave goes through walls and power falls off sharply with distance from the source. Okay, that is this thing. At high frequencies, waves will bounce off of obstacles. So, there is a limit to the distance that a radio wave can cover. VLF, LF and MF bands are limited by distance on the ground. High frequency and very high frequency waves can be bounced off the ionosphere, sending it back to earth, which is a very important thing. For example, so this is the picture. So, what might happen is that in the short wave range, you know that short wave radio, I mean you can listen to the radio transmission from USA. So, what is happening is that it is getting repeatedly reflected off the ionosphere and reaching the other end of the earth. There are problems with this wireless communication. There are problems like, so we will not go into all the details. First of all, there will be selective kind of attenuation. Then there is a thing, very irritating thing called multipath fading. So, what happens is, for example, something like this, your signal may reach directly or your signal may reach through a path after getting reflected somewhere, and these two may be out of phase. So, when they are out of phase, they will sort of cancel each other and you will have a very bad signal. So, these are the problems we encounter in mobile phones, etc. So, you have to do something about these. For microwave transmission, the transmission can be very narrowly focused. Okay. So, data can be moved from one tower to another. We have maybe you have seen those microwave towers. So, they are sort of in line of sight with each other. Alignment is important because this is a focused beam. So, if it is not aligned, your receiver will miss the signal altogether. Beams do not pass through buildings well. So, these are the disadvantages of microwaves, maybe they are disadvantages. So, if waves are delayed, they may arrive out of sync, which is known as multipath fading once again. Then finally, we have infrared and millimeter waves at the very high end of this. Of course, we have talked about optical fibers. So, they are mainly used for short range communication, they are strictly directional. So, as we are going more towards the light, it is becoming more and more directed, as light is very directed. So, they are directional, cheap and easy to use, but they do not pass through solid objects. So, you cannot use them for a mobile phone, let us say, but you can use them for controlling your TV or for short range connection to your computer from some handheld device, etc. So, so this can be an advantage or a disadvantage. That means, one way of looking at it is that since it does not go through walls, so whatever you do in one room is not going to affect whatever you are doing in the other room. So, that may be a disadvantage also. So, these are the different sort of, we tried to cover all the different ranges that we use in communication, and of course, finally, you have the satellites also, as I mentioned that you have these geostationary satellites, which are nothing but repeaters on the sky. Okay. So, we can sort of send the signal from the earth to the satellite, where it will be amplified and send it back to earth, and these satellites could be geostationary, or this satellite could be sort of low earth orbiting satellites. So, they are also used for communication over long distances. Thank you. good day. So, today we will be talking about multiplexing. Multiplexing is about sharing a medium. That means different users are sharing the same medium for communication at the same time. Okay. Now, under the simplest condition, a medium can carry one signal at any moment, because if there are two signals over there, they are going to interfere and the signal will get garbled. But for multiple signals can share one medium, the medium must somehow be divided, giving each signal a portion of the total bandwidth. If you remember that a particular frequency range around one particular frequency is called a bandwidth, and this bandwidth is the most valuable resource so far as communication is concerned. So, what we try to do is that we try to use this bandwidth somehow to facilitate the communication between a number of pairs of senders and receivers. So, that is the idea of multiplexing. The of the line increases, it becomes more cost effective for the company, and most data devices individually they require modest amount of data, but when a number of users their requirement are aggregated together, the sum total may be quite a substantial bandwidth. The current technique to accomplish this includes frequency division multiplexing, wavelength division multiplexing, time division multiplexing and code division multiplexing. We will look at many of some of these at least. So, let us see. So, this is the scheme of multiplexing. You have one multiplexer and then you have n inputs on one side. So, these n inputs are coming to the same multiplexer, they are getting mixed up in some fashion and they are being sent over the same physical link. And on the other side, depending on in which fashion you have put them together, they are sort of separated into different lines. So, these different lines on the right, they can now go to different recipients. So, just as on the left we have different senders and we have different receivers over here. So, the number of sender receiver pairs is utilizing the same physical link in between. Now, for the types of multiplexers, as I mentioned, that we have FDM, that is the frequency division multiplexing, TDM, that is the time division multiplexing, STDM, that is the statistical time division multiplexing. So, we will look at these. Just quickly before we get into the details of each of these, in time division multiplexing, each user periodically gets the entire bandwidth. That means the entire channel is dedicated to one user, but only for a short period of time, for a small burst of time. After that, it is somebody else's turn. So, we will look at the details of this later.